So in this video, we are going to look at a specific example to do with playing cards. I found that students have a hard time kind of visualizing playing cards if you're not familiar with poker or blackjack or whatever different game you may have played growing up. So here's your playing card cheat sheet. I would recommend kind of jotting this down and then going back and looking through this. But I found that the most helpful thing is this picture of the different playing card, or sorry, a whole deck of cards. So you'll see the different suits. There are 4 suits: clubs, spades, hearts, and diamonds. And then of those 4 suits, there are 13 cards of each. So there's an ace, no 1, all the way up to 10. And then you also have jack, king, and queen of your face cards, are considered your face cards. So with that being said, let's use this picture or our knowledge of playing cards, and let's answer some of the questions about a standard deck of cards. So the first question says, now we're going to find the probability of drawing each of the cards. Drawing a heart. And so the hearts, there's going to be 13 total hearts out of a total of 52. And so the probability of drawing a heart is going to be 13 out of 52, and that will reduce down to 1/4. Drawing an ace. And so when I look back at my chart, if I'm going to draw an ace, the total possible aces, there are 4 of them out of a total of 52. And so that's going to reduce down to 1 out of 13. Drawing a face card. Well, remember we said face cards are going to be our jack, king, queen. And so the number of face cards are right here. I've got 12 of them out of a total of 52. And so that is going to reduce down to 3 out of 13. Drawing a red card. So red cards are going to be all of these. There's going to be 13 of the hearts, 13 of the diamonds. So I've got a total of 26 out of 52. And so that's going to reduce down to 1/2. And then the same thing, probability of drawing a black card, 26 out of 52, which is going to reduce down to 1/2. Number 6, drawing a red face card. So drawing just a red face card, where there's only going to be 6 of those out of a total of 52. And that's going to reduce down to 3 out of 26. Drawing a 10. Of the 10s, there's going to be 4 10s. Doesn't matter what color or anything, just a 10. 4 out of 52, which is going to reduce down to 1 out of 13. Drawing a red 3. And so red 3s, there's going to be 2 of them out of 52, which is going to reduce down to 1 out of 26. And then lastly, drawing a 3 of hearts. Well, there is only 1 card that is a 3 of hearts. And so that's going to be 1 out of 52, and it doesn't reduce down anyway. So now we've got another definition: mutually exclusive events. Mutually exclusive events. Events A and B are mutually exclusive if they have no elements in common. And so some examples of that are going to be these two spinners. Essentially, mutually exclusive means you can't be both. So mutually exclusive would be anything that there's not the option to be the same. And we'll look at what that means. I know that's not a very clear definition. It makes more sense when you kind of start to see it engaged. Mutually exclusive would be like rolling a die. You can't get a 2 and a 6 at the same time. So those events would be mutually exclusive. Also, spinning a spinner, which we see on the left, the same one from the beginning of the notes. So if events A and B are mutually exclusive, then you can find the probability by adding those two together. We already did that definition earlier, but now we're just officially putting that on. This is read as A or B. So kind of make that note to yourself that or is going to be your clue to add them. And so I'm going to also highlight that operation there. And so remember when we went back to spinning that 3 or 5, we said that, well, we could find the probability of 3 plus 5, the probability of 3 plus the probability of 5, and that would give us the probability of 3 or 5. So here's another example how you could see this in the homework and on the test. If the probability of A is 0.4 and the probability of B is 0.2, I don't know what A and B are. It doesn't really matter. What is the probability of A or B? Well, we could say that's the probability of A plus the probability of B using that official formula. And probability of A is 0.4 plus the probability of B is 0.2. And so without knowing any context, I can find that the probability of A or B would be 0.6. And then we've got another definition, complementary events. Complementary events are going to be two mutually exclusive events whose sample space is the whole thing. What that means is if I had that spinner way back at the beginning of red or blue, the complement of red is blue because red and blue together take up the whole spinner. It covers everything. Snow or not snow, those would be complementary events. Rain or not rain, because it will either rain or it will not rain. There's no other option in the sample space. And so when tossing a coin, heads and tails are complementary events. When answering a true-false question, answering true, or answering false are going to be complementary events. If A has a complement, rewrite that as A with the little bar over it. Then the probability of the complement of A is 1 minus the probability of A. How this will look in a question I wrote off to the side there is it will say, what is the probability of not A? Not is going to be your clue that we're looking for the complement. So with that being said, if the probability of A is 0.3, what is the probability of not A is how we would read that. And so that theorem says the probability of not A is going to equal 1 minus the probability of A. Well, A is 0.3, so the probability of not A is going to be 0.7 because it's 1 minus 0.3. If the probability of rain is 25% or 0.25 in a decimal, what is the probability that it will not rain? Well, it's going to be 1 minus the probability of rain. And so that's going to be 1 minus 0.25. And so the probability of not rain will be 75% or 0.75. Just pay attention to how they want the answer. If it does not say, then assume a decimal. If the probability of passing a Math 212 test is 0.65, what is the probability of failing the Math 212 test? Because you can either pass or fail. Those are complementary events. And so the probability of failing a test is going to be 1 minus the probability of passing, which is going to be 1 minus 0.65, and give me a probability of 0.35 or 35% if they had asked me the answer in a percentage. And so non-mutually exclusive event examples, spinning that spinner. Let E be the event of spinning an even number and let T be the event of spinning a number divisible by 3. These are not mutually exclusive because it's possible to be an even number and be divisible by 3. And so therefore those are not mutually exclusive. And so let's list off the elements in event E, spinning an even number. So my even numbers on my spinner, not all the even numbers, are going to be 0, 2, 4, 6, and 8. The event T is spinning a number divisible by 3, and so those numbers are going to be 0, 3, 6, and 9. These are not mutually exclusive because there are numbers that overlap in both. I have 0 in both events, and then I also have 6 in both events. And so that is why they're not mutually exclusive, because there is overlap. And so if I wanted to find this probability, I could add the two probabilities together, but I would have to remove the repeats. And so what this theorem says is that you can find the probability of E plus the probability of T. Okay, so I've added those together. The probability of E is going to be 5 out of the total of 10, because there were 5 listed in my event. The probability of T is going to be 4 out of 10. Now, don't worry about reducing them yet. We'll do that at the very end. If I were to just add those together, I would have counted the numbers 0 and 6 2 times. And so what this theorem says is you're going to subtract out the numbers that are in both, the numbers that are being repeated. So I'm going to subtract out 2 of those numbers out of the 10. Subtract out 0 and 6 because they've been repeated in both sets. That's going to give you the total probability. So 5 plus 4 minus 2 is going to give me a total probability of 7 out of 10. And so that occurs, I have to subtract out the repeats when I've got this overlap of sorts. If I don't have an overlap, if the events are mutually exclusive, like rolling a die, spinning a spinner, then you don't have to subtract out the overlaps because you would just be subtracting 0. Here's a summary of those probability theorems. You need to know them. This would be something great to put on your card. I do provide them for you on a formula sheet, but this also provides them for you in a nice, concise area.